All right. So guys, let me sort of tee up the ball here for you so that you understand what we're not just doing in this unit, but the way this is going to fit together, sort of, not today, but the whole unit. So what we're doing is we're starting into a unit where we're talking about reaction rates, how fast reactions go. Do you remember when we did this last year? Do you remember the lab that we did where you took the Alka-Seltzers and you threw them in dilute hydrochloric acid solutions? And remember, you bubbled the carbon dioxide gas through a beaker of water. You put a little indicator in there and you timed how long it took to get yellow. Do you remember that? And you don't remember. And then you did it again and again and again, and you tried to make the reaction go faster. And we talked about the factors that influence the rates of reactions. Yeah, kind of. Okay. Well, guys, regardless, what we're going to do today is we're going to do some of the same stuff. But in addition to that, we're going to obviously do a much deeper dive, and we are going to study reaction rates in ways that we didn't last year. So today what we're going to do, hold on, this isn't working. Hello. Is it okay? Too loud? Is that okay? Shouldn't do that. Okay, so guys, today, no, that's too loud. I had to unplug my audio system over break and it got uncalibrated. Is that okay? It needs to be loud enough that it gets recorded, but not so loud that you guys are like, no, is it good? Okay, all right. So guys, today what we're going to do is this. We're going to start by reviewing what you learned last year, and we're going to talk about the factors that influence reaction rates. Then what we're going to do is we're going to focus on one of those. This feels loud. We're going to focus on one of the 4 factors that influences reaction rates, and we're going to talk about how reaction rates change over time. We're going to do this conceptually. We're going to do this mathematically. We're going to do this graphically. Then what we're going to do to wrap this all up, and you'll notice I underline this, you're going to learn to represent reaction rate relationships by writing what are called rate expressions. And here's the deal. You're going to find these straightforward, you're going to find them pretty easy, and you're going to forget about them. And then here's what's going to happen. You're going to forget about reaction or rate expressions, and then for the rest of this unit, you're going to learn to write what are called rate laws. So here's the way this is going to go down. Today you're going to learn to write rate expressions, you're going to do great and put them away, and then the rest of the unit you're going to learn to write rate laws, and then when you sit down to the test, here's what's going to happen. Question number 1 is going to say, well, question 1A is going to say, write the rate expression for this reaction. And guess what you all are going to do? You're going to write the rate law, because you're going to forget that we ever did these. So guys, I would make sure, you'll notice I underline this, as you're studying for the test, when we get to rate expressions in your notes, you may want to jot a note to yourself that says, don't forget about these. They're simple, but you're going to forget you ever learned them, and it's going to come back and bite you in the butt later. So again, we're going to go over what influences the rates of reactions. We're going to look at it graphically, conceptually, mathematically. Then you're going to learn to do rate expressions, and that'll be the day. You ready to go? All right, here we go. So guys, starting out, let's talk about some fundamentals, things that you need to understand, things that we've already talked about. So probably, well, you guys like taking notes, so never mind. Make sure you write this down, because that's what you guys do. All right, so guys, this is what you're learning about in this unit. You're going to learn about what is called chemical kinetics. So what are chemical kinetics? Well, guys, chemical kinetics is the study of the speeds of reactions. So how fast do reactions go? Remember last year we figured this out by using a stopwatch and an indicator and just measuring, here's how it worked. We did it sort of qualitatively. This year we're going to do it more quantitatively. So guys, when we talk about speeds of reactions, what we're talking about are what are called reaction rates. For those of you that have taken or are taking physics, you're familiar with the idea of rates. Frankly, if you're taking physics right now with Mr. Hart and doing AP physics, which is calculus-based, you may even find this a little bit disappointing because you're going to maybe start thinking about the calculus behind the rates of reactions. So let me just tell you right now, guys, in this class, you don't have to know any of the calculus of rates, not reaction rates, but we'll hint at it briefly. Okay, so this is what we're doing, chemical kinetics, which is reaction rates. So guys, this you should be able to answer. If you want to write down the question, you can, but you should know the answer to this question. So what are the factors that influence the rate of a reaction? We talked about them last year. You did a lab with this last year, but let's refresh our memory. So guys, what are the things that make a reaction go faster? Temperature, concentration, surface area, and one more, the presence of a catalyst. So guys, let's go through these one at a time and remind ourselves why. So before we get into the details, let's talk about really quickly what the underlying principle is. So guys, remember this. If you watch my hands, the idea is this. In order for a reaction between one reactant and another reactant, in order for a reaction to take place, what do these two things have to do? They got to hit, right? And so guys, what determines whether or not they react and what determines how fast they react? What about the collisions? Do you remember? How hard and how frequent. And we talked about the idea of frequency and magnitude. So the harder they hit, the faster the reaction goes, and the more frequently they hit, the faster the reaction goes. Talked about that last year. So guys, let's do concentration first. So one of the factors that influences the rate of a reaction is the concentration of the reactants. And this is the one we're going to talk about today as well in greater detail. We'll do the other three later, but we're going to do concentration today. So guys, why? Why does increasing the concentration of reactants make the reaction go faster? Is it a frequency or a magnitude issue? It's a frequency issue. So yeah, it's not putting more in there doesn't make them hit harder, it makes them hit more often. So guys, you can write down the word why if you want, but the thing that you need to write down is this is a frequency issue. So concentration influences the rate of the reaction, and that's a frequency issue. Factor number 2, temperature. And guys, you could just write down temperature. You know what? You're going to write down everything, so I'm going to change it. No, I'm going to. Here I go. Watch. I'm this crazy. Oh, no, beach ball. Why beach ball? My computer got mad at me for trying to change. Oh, gosh. Oh, that's not better. It is a sign. Do not mess with Rebecca's notes. Concentration. Oh, look at me. I'm just doing it. Temperature. Oh, look, that's gone too. And, oh, well, all right. No, you can't. You know, physical state, oh, of the reactants. All right. And, oh, look, Rebecca, it's gone right there too. Catalyst, there you go. All right. No, it's true. We did it. Okay, so guys, temperature. I know. So let's talk about temperature. We know that heating up a reaction makes it go faster. We also know that cooling a reaction makes it go slower. That's why we have refrigerators, right? Refrigerators make rotting go slower. So, guys, which one is it for temperature? Is it a frequency or a magnitude issue? It's both. So think about it. When you increase the temperature, you're making the particles move faster. That means they hit harder, kinetic energy, right? 1/2 mv squared. So they hit harder and they also hit more frequently. So temperature is like double dipping. When you increase the temperature, you get an increase in frequency and an increase in magnitude, and both of those make the reaction go faster. And temperature is the only one that influences both. So number 3, physical state. Last year you learned this as surface area. But guys, you're going to find out as we get deeper into this unit, it's not just a question of surface area. So under the heading of physical state, you can be thinking surface area right now. The reason we're not calling it surface area is because this actually plays into how a catalyst works, and we'll talk about that more later. But for right now, when you write down physical state, just think surface area. So which one is it? It's part of, yeah, so it could be solid, liquid, gas, but it could also be, is it a cube or has it been ground up? Like we did last year with the Alka-Seltzer. I think you guys are smart enough, you actually figured this out. One of the ways to make the Alka-Seltzer react quicker was to crush it. That's a surface area issue. So guys, what does surface area affect? Is it a frequency or a magnitude issue? Frequency. You've got more places that there can be collisions, so it's a frequency issue. Now you're thinking, so what if you dissolve it? That's like ultimate surface area. Yeah, absolutely. But it's not it depends on how far you spread it out, but we'll talk more later. Okay. Then guys, number 4 is a catalyst. And let me just tell you now, we're going to spend a little bit of time in class talking about catalysts. And you're going to be really disappointed at how little I know about catalysts. Guys, I think you could create a really satisfying career being a catalytic chemist. The chemistry, so here's what we're going to do when we learn about catalysts. We're just all going to be in awe of this together. I can show you how catalysts work, but I cannot explain to you why they do what they do. And frankly, I'm as amazed that catalysts do what they do as you will be. To me, it's really cool. But it's also, you're going to be asking the why questions. And guys, frankly, to understand why, the easy answer to why is polarity. But then after that, we're just going to be in awe of this together. But guys, catalysts, and you may want to write this down just so you have a definition, and Rebecca, we're going to leave it long. So guys, catalysts are spectator substances that encourage reactions to take place. But guys, they are not a reactant and they're not a product. Here's the thing you're really not going to like. They're not a reactant, they're not a product. Sometimes they're neither, sometimes they're both. Well, but what I'm saying is they're not a reactant, they're not a product. They're not one or the other. In some instances, they're neither. They're simply a surface upon which the reaction takes place. In other instances, they're both. They go in as a reactant and come out as a product without being changed. So in either instance, they're not being changed. Sometimes they go in and come out, so they're both. Sometimes they don't go in or come out. They're merely a surface upon which the reaction takes place. You'll see. We'll talk more. Oh, like, yes. Oh, yeah. No. We're gonna spend some time on that. No. You just need to know what a catalyst is. And it's foreshadowing. We're going to talk about this a lot more later. Okay, so guys, with that sort of as a review of what we did last year, here's what we're going to do today. We're going to talk about how concentration, let's just go. We're going to talk about how concentration affects the rate of a reaction. And we're going to start by defining what rate means, and then we're going to move into this, and we're going to talk about concentration and how that changes the rate of a reaction. We're going to talk about it generically at first, and then we're going to talk about it in greater detail as we go on. You ready to go? So let's define some terms. So guys, when we talk about reaction rates, the term that we need to define is speed. We're talking about the speed of these reactions. Now understand, if you've taken physics, you understand that there's a difference between speed and velocity, right? Don't worry about it. So guys, we're just going to talk about the speeds of reactions. So here's what we're going to say. The speed of a reaction or the speed of anything is change that occurs in a given amount of time. So all speeds or rates are things that are changing in a given amount of time. So guys, try this. What are examples of speeds that you interact with in your daily lives, and what are the units? Okay, so miles per hour driving your car, right? How many miles do you go in an hour? Does that mean that you have to drive for an hour to know your speed? No, but if you had gone for an hour, how many miles would you have covered? You can be going 80 miles an hour whether you go for 30 seconds or a day. But we know that in an hour you would have covered 80 miles. So guys, what are other things, what are other examples of units of speed that you're familiar with? Where do you use meters per second? Okay, so in physics class, everything's meters per second. What else?
I dropped my phone.
How far? Like you drop your phone?
Yeah, well, I'm just saying, like, on the off chance that I drop my phone, like we're doing.
So if you were to drop your phone, your first thought wouldn't be, oh crap. It would be, I wonder how fast that fell in meters per second. That's a sickness. So others, rates that isn't it interesting? It's hard to come up with some. Can I tell you the one that's most meaningful to me right now? Snow is falling right now at a rate of about 1.5 inches per hour. That's a pretty good storm. Yeah, 1.5 inches. But notice that we've got a unit of time, an hour. What else? Other rates. Say it again. Oh, one. Guys, rates that you use in your life. Oh, here we go. Here's the scary part, Cooper. Most of the people in this room have no idea what you're talking about. They don't know what that other gauge in their car is. Okay, so, yeah.
Sometimes it goes down.
But it goes faster, but I'm going slower. Okay, so guys, in your car, you've got two things that look like the speedometer. Now, seriously, I know some of you are chuckling, but every year I find people that don't know what the other needle is. It goes from 0 to about 8. There you go. So, guys, this other needle is in RPMs, right? Revolutions per minute. Most of you don't know what a crankshaft is, but it's how fast the crankshaft inside your motor is spinning, which is a result of the pistons going up and down, and then it goes transmission, driveline, tire, and it's how fast your motor is spinning, right? But what are the units? RPMs, which are rotations or revolutions per minute. Again, notice there's a time factor there, right? Okay, so guys, and there's all sorts of other units of rate, but we better just put this to rest. So, guys, here's the units that we're going to use. Because rates are always related to time, when we study the rates of reactions, we need units to do that. So, guys, we know that it's going to be in units of time, but what changes about a reaction over time? What is it that changes over time? The amounts of stuff. So guys, for now, our units of reaction rate are going to be moles per minute. Okay? So guys, our unit, for right now, our units are going to be, and let's just write this in, our units for rate right now, guys, are going to be, oops, I just ran out of space. Our units are going to be moles per minute. Understand that we're going to change this later, but for right now, our units are going to be moles per minute. You guys okay? Okay. So, guys, just trust me on this. Don't try to write down anything don't write down anything on the next slide. Just trust me. So, we understand we're going to be talking about rates of reactions. We understand that rate is dependent upon concentration, temperature, surface area, nature of the reactants, and then also a catalyst. But guys, today we're just going to talk about concentration. So, we're going to talk about this fictitiously at first. So, I lifted this out of the book. So guys, we are going to talk about a fictitious reaction, and we're going to learn some important things from this, even though it's fictitious. But we're going to talk about a fictitious reaction where A, which will be red dots, is going to turn into B, which will be blue dots. Ready? So to drive home the idea that this is fictitious, we're going to do chemistry in mason jars. We don't do chemistry in mason jars, but I love that they did this in mason jars, driving home the point that this is fictitious. But here's what we're going to do. We're going to gather some data. We're going to get some time data and some amount of A and B data. And guys, from this, and again, you don't need to write this down, we're going to learn some surprisingly interesting things. So first of all, assuming that the reds and the blues are atoms or molecules, guys, what units do we use when we count amounts of atoms or molecules? Moles. Okay, so here we go. Times 0. So guys, this mason jar on the right represents times 0. So we're going to say that all of the dots that are inside this mason jar represent 1 mole of A. Okay, it should be Avogadro's number of dots, but that's crazy. So we're going to say this is 1 mole of A. But guys, let me zoom into this so you can see it maybe a little better. So if that's 1 mole of A, how much B is there at times 0? Why is there 0 B? What is B? Blue, but what is B? It's the product. And guys, how much product do you start with initially in a reaction? None. So guys, we have no B when the reaction starts. It's a fundamental principle. When a reaction starts, you start with reactant, you've got no product. Does that make sense? Okay, now we're going to go 20 minutes later. And guys, they actually did the counting for you. So I'll give you numbers, but let's talk generically. So 20 minutes later, A is turning into B. So how much A is there going to be after 20 minutes relative to 1 mole? Less, right? Reactant gets consumed as a reaction goes on. So guys, after 20 minutes, they did the counting, and there were 100 dots. Now there's 54 dots. So there's 54, there's that fraction of a mole. So now the question is this: how much B is there going to be? Yeah, so guys, do you see that? That there's going to be 0.46 moles of B. What is the take-home message from this? What happens to A over time? Turns into B. So guys, in 20 minutes, we had 46 hundredths of a mole of A turn into B. So we have 0.54 moles of A left and 0.46 moles of it turned into B. You get the idea? Here's the important point then. Guys, what happens 20 minutes later? After another 20 minutes, did we lose another 0.46 moles of A? Uh-oh. Who said that? Is that down? Say it again. It's a half-life. Guys, these are half-lives. We will relate this to half-life equations later in the unit. But guys, for right now, and it's cool that Dallin made that connection, and he's absolutely right. This is a half-life-like relationship. But guys, the idea is this, that after another 20 minutes, we do not lose another 0.46 moles. The number is actually, we go down to about 0.30 moles. So how much B will there be? 0.7 moles. So guys, you need to understand what you're seeing, and then we've got to explain it. So over time, what's happening to A? It's turning into B. But over time, what is happening to the rate? There's our important term. What is happening to the rate at which A is turning into B? It's slowing down. And guys, you may want to write this in your notes, because this is a universal truth. All reactions slow down over time. Assuming that we're not doing anything from the outside to stoke the fires, so to say. Guys, all reactions, just a second, all reactions are slowing down over time. And if you wrote that down, all reactions slow down over time. Now add the word because. And guys, now let's talk about the because. Why? Why are these reactions slowing down over time? Go ahead, Rachel. Okay, but keep going. If you want to think about it that way, go. But I'm going to take us back even deeper, but go. That's the connection. But understand, half-life describes it. It doesn't cause it to happen. Do you see what I'm saying? But it is described, as Dallin initially got us thinking, it is described as a half-life relationship. But say the second thing you said, because that's the important why. Why does it slow down? Do you guys get that? Would you write it in your notes? Guys, the reason these reactions slow down is because the concentration of what? The reactants is always going down. Guys, these reactions consume themselves. They are literally destroying themselves. The reactants are being consumed. And one of the things that we know that determines the rate of a reaction is how much reactant there is. And initially we start with a lot of reactant. Mark, I think you said the word frequency. Guys, when we start at the beginning, there's a lot of A, and it's all running into each other and it's turning into B. But now when we get over here, there's less A. And because there's less A, they're colliding less frequently. And as a result, because the frequency of collision goes down, the rate goes down, and the speed at which A turns into B is always slowing down. So the big idea, guys, as Rachel said, is because the concentration is going down, the rate goes down because the collisions are less frequent. Do you get the idea? Now let's just say this right now. For those of you that have done this relative to calculus, do you see the connection that this is a first derivative? That we're looking at change over time, the rate at which this is changed. So concentration, we don't have to get into it a lot, but let's just say this. If your brain is starting to think that I could be taking derivatives to figure out rates of change, you're right. We just don't have to do it. So guys, let's do this and then we'll answer questions. This is what you've got to understand right now. Unless you do something externally, all reactions are slowing down because the concentrations are going down because the reactants are being consumed and turned into products. Are you comfortable with that? Then we're going to gently try questions. Go ahead, Jake.
I was just going to say, like, this is where the book mentioned instantaneous.
We're going to do that in just a second. We're going to look at the instantaneous versus the average rate. We're never going to do instantaneous rates in here. Understanding that you could find the instantaneous rates through derivatives, but we don't need to do that. So is that helpful for you if you're doing the calculus? Because you could figure out instantaneous rates. We just don't need to do that. So guys, are you solid on the idea? You get the idea? Okay, so now watch this. Let's refresh your memory. Here's what we said. What is happening to the amount of... Don't touch the board. What is happening to the amount of A over time? Going down. What's happening to the amount of B over time? Going up. What is happening to the rate at which A is turning into B? Slowing down. So now guys, imagine this. We are now going to graph time versus amount. Okay? Think about this. Time on the x-axis, amount on the y-axis. So guys, amount of both. So what will the curve look like for A? Do we start with a little a or a lot of A? A lot of A. So will this go down linearly? It doesn't. It's a curved relationship. Now what about B? Do we start with a little or a lot? Start with none. And it's going to go up, but also a concave relationship. So guys, this is actually what the graph of this data looks like over time. Do you see it? So look at what we're seeing. We're seeing that initially, well, let's do this. Which one of these is our reactants, red or blue? How do you know it's red if you didn't actually have the mason jars to look at? Because you start with some. So guys, your reactants will always be up here because that's what you start with. Your products will start at 0. And then guys, notice initially a very steep, right? We need to be able to do steep, whether or not we can do the calculus of it. So guys, you'll notice here, this is very steep. So a steep line means a fast rate. And then as time goes on, the steepness of the curve is decreasing because the slope of that line tells us the rate of change, because that would be the number of moles over time, and moles over minutes is our measure of rate. So slope is rise over run. So here it's very steep, meaning it's going fast, and then you'll notice it goes down and it becomes more horizontal, meaning the reaction slows down. Does that make sense? Then conversely, you'll notice the opposite happens with the amount of B, because that is going from 0 up, but this relationship is inverse of each other. As one is consumed, the other is created. Do you get the idea? Okay. So guys, if you understand that conceptually, now what we've got to do is we've got to describe it mathematically. So this is the equation that we are going to use to describe rate. So guys, rates for our reactions are going to be in moles of B, change in moles of B over change in time. And so probably all that you need to write down is this, because you guys understand that delta means change, right? And guys, I don't know if you need to write this down, but I put it in the notes. Do you remember, how do we figure out changes? Is it initial minus final or final minus initial? It's always final minus initial. So guys, the change in moles of B is moles final minus moles initial. The change in time is time final minus time initial. It's always final minus initial. And that's the thing that I wanted to talk about before we move on. Guys, when we do rates of reactions, we will always track products. We will not track reactants. So that may be worth, I don't know if you want to, I don't know, however you would highlight that in your notes. But guys, we always track products when we're talking about reaction rates. You guys okay? Can I get rid of this? Okay, so here's what we're going to do. We're going to break into teams. Yay, go team. So guys, what we're going to do is this. We are going to figure out the rate of this reaction in 10-minute intervals. So we've got 6 of those, and we've got 6 groups. So let's do this. So Dallin, guys, so everybody that you're sort of next to in your little aisle there, you're going to be a part of a team. You're going to do this individually and then compare numbers. So Dallin, your group is going to figure out the rate between times 0 and 10. Rebecca, you guys are going to go 10 to 20. So Bradley, if you would do 20 to 30. And then Valeria, we'll have your team go 30. We'll have your team go 30 to 40. And then Matthias, if your team, well, you and Tracy, if you would do 40 to 50, and then guys, if Joel, if your guys would go 50 to 60. So guys, just do it on your own, but then if you want to compare answers, figure out the rates of these reactions. Again, 0 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 50, 50 to 60. No, because, and that's the point, we're only doing this for B. Just for B, our rates of reactions will always be relative to products. Oh, and notice, guys, you've got your data points. They give them to you. So, yeah, the concentration, or I'm sorry, the amount of B would be 0.26, 0.46. They give them to you on the line. Here, I can zoom in so you can see it better. Yes.
Hi. Now let's screw basic math. We don't need that.
You guys all got your numbers? All right. So guys, the first thing we need is an equation which none of you wrote down. So rate is equal to change in B, change in time. So guys, I'm going to run the numbers for group, well, for Dallin's group, it's the first group. So looking at our change in B, from 0 to 10, it goes up to 0.26. So our final amount is 0.26 moles. Our initial amount is 0 moles. And then our time is from 10 minutes down to 0 minutes. So functionally, we've got 0.26 moles divided by 10 minutes, which would be 2.6 moles per minute. You guys agree? Did I do it wrong? Oh, sorry, 0.26.
Same thing I did, Mr. Nussberger.
I lost my decimal. So 0.026. Okay, all right. So I'm going to collect data then. So trial number 1, 0.026. And again, that's moles over minutes. So Rebecca, what did your group get? 0.020. Bradley? You were doing 2 to 3. So your numbers went 0.014. Larry, what did you guys get? 0.010. Brandon? Okay. So guys, does this bear out what we understand? So these numbers are rate numbers. So this does not tell us that the amount of B is going up. It doesn't tell us the amount of B is going down. It doesn't tell us about the amount of B. It tells us about how quickly B is being created, how it's being formed, and what is happening to the rate at which B is being formed. The rate is going down. These are our rate numbers, and we see the rate at which this is going down is going down. Now guys, here's the thing. I know some of you are trying to look for the relationship here, that you're thinking, wait, it went down by 0.006, 0.006, 0.004, 0.008, or 0.002, 0.002. Guys, understand the rate at which it's going down is going down. The reason that we're not seeing that very cleanly is because of rounding errors, and frankly, because we're using numbers that are made up from some stupid mason jar. But here's what we know. We know that when we do rates, we are always going to track how quickly the product is formed. We also understand that our rates will be decreasing because, as we said, the concentrations are going down, the frequency goes down, the reaction slows down, and we can see that as the rate decreases over time. You guys good? Okay. So guys, with that said, these are not the units that we're going to use for reaction rates. And you probably picked up on this. I heard some of you say this. So let's talk about why. Guys, when we measure rates of reactions, using moles and using minutes are both completely worthless to us in lab. So let's talk about the easy one first. Why are minutes not a good unit of time? It happens way faster than that. So guys, instead of minutes, our units for rate are going to be in seconds. But also, why is moles a bad choice? And what would be a better thing to do in lab? Say it again. We can't measure moles. Guys, we do not have a molometer. We have no way to measure moles. So what do we do in lab in order to measure moles? We measure mass and then we convert. So guys, why would measuring mass in lab be a bad idea? What are we talking about the mass of? The mass of, oh, I see what you're saying. So either we weigh the mass of the entire reaction, but we know that that should stay the same because of the law of conservation of mass, or we would have to tease the product out of the mixture and then weigh it. But guys, in order to do that, we'd have to hit it like a pause button, stop the reaction and weigh the product, and we can't do that. So guys, moles don't work. So what are we going to use instead? Molarity. So now you're asking yourself, why is molarity a better choice? You're going, wait, if we can't measure moles, wouldn't molarity be worse because molarity is moles over liters? And now we've got two things. We've already said we can't measure moles, and now we got to measure liters, and that's hard too. So why is molarity better than moles? Well, guess what? We can measure molarity and not have to mess with the reaction. How do we measure molarity? Say it again. One of the ways we can do it is Beer's law. Shine a light through it. Remember the lab, y'all? Shine a light through it. And remember, the higher the concentration of product, the less light we'll get through. We can use, remember the spectrometer? We can shine a light through the reaction, and we can directly measure the molarity of the reaction as it's going on just by shining a light through it. And as the concentration of product goes up, less light goes through, just like we did with Beer's law. But guys, there's another way that we can directly measure molarity. Do you see it? All right, this could be a little obscure. pH. Guys, what is pH? pH is the negative log of what? Do you remember? Hydronium ion concentration. So guys, this is what we're going to be doing in the next unit, is we are going to be measuring the rates of reactions by measuring changes in pH, because pH is a direct window into the concentration of hydronium ion, so we can measure reaction rates for acid-base reactions simply by knowing the pH. Yeah?
So, I mean, is that just like pH, changing pH per minute or per second? I mean?
No. We'll know the pH, we'll convert that to molarities, and then it'll be molarity of hydronium ion over time. Yeah, so we don't measure it in pH over time, although we could, but we'll convert to molarities and go from there. So guys, bottom line then is this, and this is sort of a summary of what we've just said, that we are not going to use moles. We're not going to use moles per minute. We are going to talk about molarity per second. So those will be our units. All right, so with this in mind, guys, and you already got molarity per second, right? Let's look at another set of data. This is what our data is going to look like when we talk about reaction rates. You ready? Looks like this. So we're going to talk about the reaction of a substance called butyl chloride reacting with water. Please don't write any of this down. I just want to familiarize you with how we're going to deal with data for the rest of this unit. So guys, this is the reaction we're talking about. This is butyl chloride. That, as you know, is water. And this produces an alcohol called butanol, and then it forms hydrochloric acid. So guys, when you see the reaction data for this, the rate data for this, it will actually look more like this. So what we're going to do is they actually track the concentration of a reactant. I don't know why they did that in this case. You'll see for the data that we're going to look at, we'll be tracking product data. But we'll talk about the differences in just a second. So guys, this is the data. Again, for this one, for some reason in this data, and again, can you see that okay? Do I need to zoom? I'll zoom, but let me get a writing tool first. So guys, it goes like this. rather than track the concentration of a product, for some reason they chose to give us data where they're tracking the concentration of a reactant. So initially, this had a concentration of 0.1 molar. So guys, notice what happens over time to the concentration of the reactant. So over time, the amount of reactant is going down as we expected, the reactant's being consumed. But guys, notice then that we can calculate, just like you did with our mason jar data, we can figure out rates. It's just change in this case, reactant, and change in time. So you take the two concentrations of reactants, final minus initial, the time difference, which is 50 seconds, divide them, and what they've done is they've gone through and they've calculated the rates of the reaction for each of those time intervals. Notice what they did though, which is weird, but it's good. They left them all in relationship to 10 to the negative fourth. So by not making these down here 10 to the negative fifth, we can compare the numbers and look at what's happening. Initially, the reaction was going at 1.9 times 10 to the negative fourth molarity per second, then 1.7, 1.6, 1.4, 1.2, 1.8.56. The reaction is slowing down over time. You get the idea? Reinforcing what we talked about? So guys, here then's an interesting question. What if we were to go back and actually collect data for this reaction looking at this instead? What if instead of looking at the rate at which the one is consumed, what if we were to look at the rate at which that is produced? What would these rate numbers be? The same, but opposite. The sign would change. Because guys, if one of them is being consumed, the other one has to be created. So if one's going down and we're calling that positive, then the one that's being created would have to be the opposite. It would have to be negative. So guys, the important thing that you need to understand is this. The rates of these two things, the rate at which this is consumed and the rate at which this is created, the rates are the same, but the signs are opposite. Does that make sense? You get the idea? So if you know the rate at which something's being consumed, the rate at which the other's being created will be the same rate, but it'll have the opposite sign because one's being consumed and the other's being created. Does that make sense? You okay with that? Okay. But guys, here then is the question and the last thing we need to talk about today. What is it about this reaction that tells you that those rates are equal? Why is it that those rates are equal? Yeah, it balances with all ones. So guys, for every one of these that gets consumed, one of these gets created. So because this balances with all ones, the rate of consumption is equal to the rate of creation. Yeah.
I think the half-life, so you could never get rid of the reactants completely in half-life, so why are they not the product as well?
Let's talk about that later, because what you're going to find, we're going to relate this to half-life in a couple days, and what you're going to find out is that reality and the way we represent it aren't exactly the same. And unlike when we talked about half-life, when we were talking about radioactive decay, this actually can be completely consumed. We talk about it as going to zero. So you'll see, we'll talk. Yeah. Exactly, yeah, and that's kind of what they're representing here, where they're saying this goes to zero after a whole lot of time. Eventually, we do, unlike the way we did half-life with radioactivity, we think of these as going to zero. Yeah. Okay, so guys, back to the thing we were talking about. Do you understand that this is, the rates are equal because it's all ones? So now the question is, what if it's not all ones? And the answer is, this is where you need to learn to write what are called rate expressions. Guys, rate expressions allow you to figure out the relative rates when it doesn't balance with all ones. So this is where you want to start taking notes again, guys, right here. So what are rate expressions? No, that's what we're going to talk about. Yeah, no, we're going to answer that. Not for now it's rhetorical. Rhetorical. So what are rate expressions? And again, guys, remember what you were going to write over here about don't forget these? And the reason you're thinking don't forget these is because, guys, this is the only time in this class that we're going to write rate expressions except for the test. And everything that we're going to do for the rest of this unit, you're going to be writing rate laws. And you're going to forget about rate expressions, and you're going to get really good at writing rate laws. And then on the test, it's going to say oh gosh, okay? It's going to say write the rate expression, and you're going to forget about rate laws. So guys, what are rate laws? Or what are rate expressions? Rate expressions are representations of stoichiometric relationships. Remember, stoichiometric relationships are just the ratios from a balanced equation. But guys, here's the problem. In the two examples that we looked at just now in class, the stupid mason jar thing, and then also the butyl chloride reaction, the rate of disappearance and the rate of appearance were 1 to 1. The stoichiometric ratios were 1 to 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 1. It was all ones. But guys, what if it's not ones? Well, I'm going to show you. I was so proud of myself when I figured this out. You're going to love my... No, you're not. You may love my animation. All right, you ready? Don't try to write this down because this is so mesmerizing you won't be able to. So you ready? Mason jars, right? What did A turn into? B. But what if A turned into 2 B's? Then what would the relationship look like? You ready? Check this out. So guys, in order to, and to represent this, we're going to write a rate expression. But to write a rate expression, we need to account for the fact that B is being created twice as quickly as A is being consumed. So here's the idea. Say that we start with some amount of A, like in our first mason jar, right? Check this out. And as the reaction takes place, 1A goes away. See how it's below the line because it went away? But when 1A goes away, what gets made? 2 B's. Huh? And if we lose another A, huh? We get 2 more B's. And what if we lose another A? Then we get 2 more B's. Get the idea? So, I know, touching. Now, oh, I get it. But guys, the thought then becomes this. If A is going away at half the rate that B is getting created, in our previous examples, when it was 1 to 1, we knew that the rate that one was going down was equal to the rate that the other was going up. But what do we have to do if we want these to be equal? Because we have a rate at which A is going down, and we have a rate at which B is going up, but these aren't equal. They're headed in the opposite directions, and this one is growing faster than that one is shrinking. So here's the question. Guys, equal really means equal. So what would we have to do to these piles of dots to make them equal? Well, so first of all, rather than multiply this by 2, we're going to divide this one by 2. But the first thing we got to do is flip this one over. This one's going in the wrong direction. So we're going to flip it over by making it negative. And when we make it negative, it changes the direction. So the first thing we're going to do is this. Guys, why was A going down? Because it's a reactant. It's being consumed. So when we write rate expressions, we're going to make the rate that A goes down negative, which changes its direction. So now it's headed in the right direction. But now we've got to make this the same height as that. So what are we going to do? Divide that guy by 2, and now they're the same. So guys, the bottom line is this. When we write rate expressions, we'll make the rate expression for the reactants negative. That flips them over. And then we'll divide by the coefficients to make them the same heights. So with that in mind, guys, this is the way this would look. Write this down with me. So here's how you write rate expressions. This is just how you calculated rate before, change in concentration, change in time. So rate is equal to the change in concentration of A over the change in time, and that is equal to the rate of change of B divided by the change in concentration of B over time. But now, guys, we've got to make these equal because we know that they're not equal. So how do we head A in the proper direction? A is going down. How do we make it go the other way? Make it negative. So put a negative sign in front. And now how do we account for the heights? How do we make this as tall as that? Divide that by 2. No, and that's the point. So the idea is this. Universally, make the reactants negative, and then put the coefficients, whatever they may be, in the denominators.
So if you have a 2A for 3B,
Yeah.
you put the 2 underneath.
Exactly, and we're going to look at an example like that in just a second.
Is there a convention for the radiation for coefficient?
Yeah, that's fine. But let's just apply it and you'll see. So guys, on the test, again, this is what you're going to forget. You could see something like this. Write the rate expression for this reaction. 2HI decomposing into H2 and I2. Go for it. So if you're not sure where to start with rate is equal to. No, now we're using the actual reactants. Yeah, this is no longer generic. You do all three, yeah. And guys, that's when you write rate expressions, you write them for the whole thing. And then what you'll see in homework is after you write the rate expression, you'll plug data into it and solve. So can we look at it? So what's this going to look like? Well, first of all, we need to know the rate for HI. So because this is a reactant, what are we going to do? Make it negative, and what are we going to do with the 2? Divide by it. So it would look like this. So negative, the change in concentration of HI divided by 2 times the change in time. So guys, the idea is this. This is the rate component. Change in concentration, change in time, and then this and this are the things specific to this balanced equation that will actually make these equal. So because it's a reactant, we make it negative, and then we bring the 2 down here. Is that okay? So now we need to look at our next component. So that is equal to this. This is now our product. So we don't make it negative, and there is no number in front. We just leave it like that. What if there had been like a 3 there? Then we bring down there. And then that is equal to change in concentration of I2 divided by change in time. Yeah. Correct. Right. Yeah. So let's do this. So what are we going to do with this? So for example, what they would do for you or to you or whatever in a homework question would be something like HI is being consumed at a rate of 1.5 molarity. Well, here, let's do it like this. 1.5 molarity per second. Okay, so at some point, HI is being consumed at this rate. At that same moment, what rate is I2 being formed? Do you see what we're saying? Do you guys, I'm just making this up, but do you see? This is what this will look like in homework. So they'll say, at some moment in time, HI is being consumed at a rate of 1.5 molarity per second. At that same moment, how fast is I2 being created? So the way to solve that would be, first of all, get rid of this. This isn't pertinent to the problem. But then what you do is this. We are given this. We are given the rate at which HI is being consumed. So that's negative 1.5 molarity per second divided, well, actually, let's do it like this. So it's 1.5 molarity per second. So it's negative 1.5 molarity over 2 seconds. Do you see that? And that is equal to, we want to solve, we said for I, we want to solve for this. So that would then be our x. That's what we want to solve for. So it would simply be negative 1.5 divided by 2. So the answer would be negative 0.75 molarity per second. Does that make sense? Yeah. You're solving for the entire term, exactly. Yep. Is that okay? So that's the idea. So the rate at which that is being created would be 1.5 or 0.75 molarity per second. Is that okay? Yeah.
Would you write the change in concentration of I?
You could, yeah. I mean, but it's asking you to solve for it. And you're identifying it as your x, so either way is fine. Why is that negative, though? Oh, that's why this should be negative, because that's being consumed. So the rate of that should be negative to begin with, and then the two negatives make that positive, meaning that should be positive. I was like, wait, that shouldn't be negative. But the idea is that that rate is a rate of consumption, so final minus initial would make it negative. Yeah. Well, but understand the delta T accounts for this unit because it's change in molarity over change in time. Because these are rates, they're changing. Okay. But if it's helpful for you mathematically, understand that like on the test, if you were being asked to write the rate expression, you would have to write the deltas because this is a rate, so it's changing. But then when you solve them, if you don't include it, you're fine. Is that okay? You guys okay? All right. So guys, here we go. This is what we got for tonight.